So welcome everyone back to on randomness and order in geometric, extremal and structural graph theory mini symposium. Our first speaker of today's session is Alexey Pokrovskiy, who is a lecturer at UCL. Thanks Alexey a lot for agreeing to talk. And he will talk on isomorphic cubic bisections.
Thank you, Liana and Andre, for the invitation. A very nice workshop. So I want to tell you about a joint work with Shagnik Das and Benny Sudakov. And this is going to be about cubic graphs. So the whole talk will be about cubic graphs. Just to remind you, a cubic graph is a three-regular graph. So all vertices have degree 3. So two examples is the three-dimensional cube, which is probably where the name comes from, or the Peterson graph is also another common example. So, and what the talk will be about is it'll be about partitioning the vertices mostly of the cubic graph in such a way that, basically for coloring the vertices of a cubic graph in such a way that the induced subgraphs on the monochromatic sets have a nice structure. The simplest theorems like this, or the most powerful theorems like this, are about proper coloring. So a proper coloring of a graph is a coloring of the vertices such that the monochromatic sets are independent sets. So they sort of have the simplest possible structure. And what we know about this if we're looking at cubic graphs, so Brooks' theorem, the special case of it for cubic graphs, tells us that unless you're K4, you can color every cubic graph using 3 colors. Right, so something like this. Okay, so that's what Brooks' theorem tells us. You can get 3 colors which are independent sets, and Wising's theorem says something similar about edge coloring. You can always 4-edge color a cubic graph to get independent sets. Okay, and what the talk will be about is about if you use less colors. If you use less colors than these numbers, then you can't anymore guarantee that the colors are independent sets, but maybe you can still guarantee that the colors have some nice simple structure to them. So that's what the talk will be motivated by. And there's lots of different directions from which you can try and come at this. So one is to ask for the colors to have small size. And there's a simple proposition here, which is that you can always 2-color a cubic graph. So using just now colors red and blue, such that the monochromatic sets are matchings. So in this case, it will look like this, right? See, I've used 2 colors, and if you look at the monochromatic sets, that's one, that's one, that's another one, and they're matchings. So this is very easy to prove. So the proof is just a couple of lines. It goes like this. So color the graph so that the number of monochromatic edges is as small as possible. And that will give you that the monochromatic sets are matchings. So the reason this happens is, say for contradiction that you had 3 vertices with 2 edges like this between them. So if you had something that wasn't a matching, it would have to have a degree 2 vertex. So think about the 3rd edge here. Whichever color you get here, as if you recolor this central vertex, you'll decrease the number of monochromatic edges, right? So at the moment, there's 2 of them. If you color it to blue, you'll have 1 at most, right? So that shows you that if you have the minimum number of monochromatic edges, then you have to have matchings. So this is the kind of thing that we're interested in today. So this is about coloring the vertices. If you're coloring edges, something analogous was proved by Thomason, who said that if you just use two colors, you can color the edges of a cubic graph such that all the monochromatic components have paths of length at most 5. So this is a much harder theorem. It actually improved on several earlier results, which were about getting paths which are longer than 5 potentially, and it even solved the conjecture. So this is a reasonably deep theorem, this Thomason, in contrast to the vertex version. So the motivation for what I want to talk about today is a version of this proposition about two coloring the vertices, but a version of it where you ask for there to be the same number of red and blue vertices. So here's a conjecture of a Ban and lineal, which says that it says that in the proposition on the last slide, you can color the cubic graph in such a way that you have the same number of red and blue vertices. So there is an equal number of red vertices and blue vertices. Of course, for this to hold, you need an even number of vertices overall, which actually holds for all cubic graphs, because you can't have an odd degree and an odd number of vertices in a graph. And there's a single exception in this conjecture, which is the Peterson graph. So first of all, why did they make this conjecture? So Ban and lineal, in their paper, they were investigating things called internal partitions and external partitions of a graph. So an external partition of a graph is a graph where is a red-blue coloring of it, so that you have, from every vertex, you have more edges going outside its color class than within its color class. And for a cubic graph, an external partition with the same number of red and blue vertices is exactly what this conjecture asks for. So that's kind of how they came at this conjecture. What's known about it? So it's known for some special classes of graphs, like 3-edge colorable graphs and claw-free graphs, and also for small graphs. And for general graphs, the best we know is that you can color red-blue color the vertices of a general graph so that the monochromatic components are paths of length at most 2, whereas the conjecture asks them for paths of length at most 1. Okay, so that's this conjecture. And what we looked at with Benny and Shagnik is a kind of a weakening of this conjecture. So this talk will be about proving a weakening of this conjecture, but it's a weakening in quite a weird direction. So it's quite kind of like the weakening isn't really in the spirit of this conjecture as such. So to explain where the weakening comes from, we need to observe that in this conjecture, the number of red edges and blue edges is always equal. If you give a coloring which satisfies the conjecture, you'll always have red matching and the blue matching having the same size. And the way you see this is the number of red edges. So this is just an edges which have both endpoints in the red. So this is the red vertices, this is the blue vertices. So we're counting now edges which have both of their endpoints in here. So this is going to be equal to 3 times r, which is the number of edges leaving r, minus the number of edges going between r and b, and divided by 2 because you're double counting all red edges in this expression. And of course, because r and b have the same size, this is equal to 3 times the size of number of blue vertices, minus the same number of edges between r and b divided by 2, which is equal to the number of blue edges. So from this, we get that if you have a graph which satisfies this conjecture, then the red matching has to look the same as the blue matching, and that it has the same number of edges. So in other words, we kind of get isomorphic matchings in each color. And a weakening of this is to just ask whether you can partition the graph, you can color the vertices using red and blue such that the subgraphs you have in R and B are isomorphic. This is something that Ando conjectured. So basically a weakening of this conjecture where you don't ask for the color classes to be matchings, but instead just ask them to be isomorphic. One motivation for this is that it's a weakening of the bilineal conjecture. Another motivation is that it's kind of a version of a conjecture which was made earlier by Wormald, that essentially an edge coloring version of this. So Wormhold's conjecture here is about two edge coloring a cubic graph such that the red and blue graphs are isomorphic again. And Wormhold asks for a bit more. It doesn't just ask them to be isomorphic, but asks them to also be path forests. So that's the second motivation for Ando's conjecture. So what's known about Ando's conjecture? Like all the classes of graphs for which we know it are the ones for which we know the bilineal conjecture. There's been very little direct work on this conjecture. But there is a paper of Abro, Gojeber, Labat, and MoCCA'20, which first of all, it proves various kinds of results about this conjecture. It verifies it for small numbers of vertices, and it also draws interesting parallels between these two conjectures. So it shows that under some situations, if you can solve one conjecture on a graph, you can solve the other one. And what I'll tell you about today is with Shagnik, Das, and Benny Surikov, we proved Ando's conjecture for sufficiently large cubic graphs. So this is the proof I want to present. So the difference between this and the actual conjecture is here we asked for the graphs to be sufficiently large and also connected. So this is what I'll be talking about. So what do I want to say about the proof of this? It's a little bit like an absorption argument in that we first start with two coloring in which the red and blue graphs are not quite isomorphic, but very similar, and then we modify it to make them exactly isomorphic. So it's, in that sense, it's a little bit like an absorption argument, although the setting is quite different from where the places you normally use absorption. So the starting point is we want to find a coloring of the vertices red and blue such that the red and blue graphs look very similar. A natural coloring to use for this is to just randomly, independently color every vertex red or blue. So you take a cubic graph, you independently color the vertices red and blue, and we want to prove that the red graph and the blue graph looks quite similar to each other. How can we measure similar? So one way that's useful for us is to measure the number of, for any small graph H, to measure the number of red copies of it you have and the number of blue copies. And it's easy to show that these two numbers have to be almost the same. So the way you see this is, so if you want to count like the expected number of red copies of a graph, this is going to be equal to, so if the original graph, if the whole graph you're looking at has m copies of H, then the expected number of red ones will be m divided by 2 times the number of vertices of H, which is of course by symmetry is also equal to the expected number of blue copies of H. So the expected difference between these two quantities is 0, and this random variable is concentrated around its expectation. You can use, say, Azuma's inequality or McDermott's inequality to prove this. So that proves this lemma. So this lemma, so once you have something like this lemma, you want to take the coloring which satisfy this and somehow recolor parts of it in order to get rid of this error term. If you could get rid of this error term, then the two classes have to be exactly isomorphic. So that's what you want to do next. So for us, it was more convenient to not use this lemma exactly, but use a variant of it, which I'll next present to you. So the issue with using this lemma directly is that, so if the error term here depends on the size of the graph H, it depends on the graphs you're counting, and the number of, if H is really very small, then this error term will be small, but potentially if you just look at a random red-blue coloring of a cubic graph, some of the components will be reasonably large, which can cause a little bit of problems. So next I'll show you a version of this lemma, which is basically the same, except it doesn't have any large components. So all of the components end up having bounded size. So here's the version. So it says that every cubic graph can be colored so that all monochromatic subgraphs are paths of length at most 5. So if you look at any monochromatic subgraph, it's a component rather, it's always a path of length at most 5. And then also everything is concentrated. So the number of copies of every graph is concentrated like before. This is what I'll present next. So the proof of this, it's based on a theorem of Thomasson, which I mentioned on the first slide. So recall that Thomasson proved, what did he prove? So if we go back to the first slide, you can color the edges of every cubic graph, the edges now, so that the monochromatic graphs are paths of length at most 5. So this is something we use here. So Thomasson said that you can partition the edges of G. So the edges of G can be partitioned into two subgraphs, F1, F2, which are both path forests, so unions of disjoint path with paths of length at most 5. So this is what this theorem of Thomasson I just mentioned does. Okay, now how can we use this? So let's just focus on one of these forests, say on F1. So what it'll look like, here's a path of length 5. There might be a path of length 4, so it'll just be a disjoint union of paths like this. Maybe some isolated vertices. And we'll randomly...
Alexey, just a quick question. So when you say path of length 5, you mean vertex length or edge length?
I mean edge length. It doesn't really matter.
Yeah, okay.
Right. So we'll now randomly color the vertices of the graph. So randomly color each of these paths properly, meaning we give each path here proper coloring, meaning just that the edges get different colors. So maybe this path gets colored like this, this one gets colored like this, and so on. So each path has exactly 2 proper colorings, right? Because it's a connected bipartite graph, and you pick one of them at random. Okay, so this is the coloring we'll use for this lemma. So why does it end up having these properties? So this red property, it doesn't use any randomness to get this. This just comes from the fact that we build this coloring by coloring the paths in F1 properly like this. So the monochromatic components must all be contained in the second linear forest or path forest that we started with. So why? Because all of the edges of the original graph are partitioned into these 2 path forests, but in F1, which I've drawn here, there are no monochromatic edges. All of the edges go between a red vertex and a blue vertex. So all the monochromatic edges have to be in the second forest. And because the second forest also has paths of a length at most 5, you get that all the monochromatic components you get are paths of a length at most 5. And so that does this part of the lemma. The second part that you have this.
Sorry, do you mind doing this a bit slower?
Yeah, sure. So where this first inequality comes from. So let's draw a graph, say the Peterson graph. So Thomason gives us a partition of this graph into two of the edges of this graph into two path forests. Let's hope I can do this. The remainder path forest, not quite. Yes. Okay, that's one path forest. And here's another one. Okay, so let's say green is F1, which is what one path with 3 edges and one path with 4 edges. Hopefully you can see them. Now we randomly color each of these two paths using red and blue. So say this one gets red, red, blue. This one gets red, 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 blue. And now let's draw get a vertex coloring of the whole original graph now. So this one's red, this one's red, this one's blue, this one's blue, and the same for the other one. Red, red, red. No wait, oh, messed up. Red, 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 blue, blue. Okay, so that this way we got a coloring. And what are the monochromatic edges? Let's find them. This is monochromatic. Actually, this is another color. This is monochromatic. It's blue. This one's monochromatic. It's red, and that's it, right? And notice the monochromatic edges are all contained in the pink graph from the original edge coloring. And this just happens because all of the edges in the original graph were either green or pink, and the green edges, they all got different colors on their endpoints because of how we constructed the coloring. So therefore, all of the monochromatic edges have to be pink. In other words, they're contained inside F2, which tells us that because F2 was a union of path forest with path of length at most 5, the same has to be true for these new monochromatic edges we got. Does that help?
Yes.
And this concentration thing, it comes out the same way roughly as it did in the truly random coloring. It's a similar kind of concentration inequality. Okay, so now let's, this is the starting point kind of for proving our theorem. We got a coloring where all the monochromatic components are small, and they all also look, the red graph looks a lot like the blue graph in that you have almost the same count of monochromatic paths. We combine this with a recoloring approach where we change the numbers of the various small paths until all of these error terms disappear. And I'll only sketch to you how to do this. So we need a lemma like this one. So it's a little bit complicated. I'll just give you an example of what it's saying in a second. But what it's saying is that inside a cubic graph, you can find a small subgraph, so a constant site subgraph with 2 colorings. So 2 special colorings, which have a bunch of properties. And the properties are basically that the colorings look almost the same, except the numbers of some particular small paths change slightly between the 2 colorings. So I'll give you an example of a graph which has these properties. So this will be for k is equal to 1, 2, 3. So basically, there'll be 2 colorings of this graph, and the number of red P3s will change between the 2 colorings. So this is one coloring. It has a single red P3, and this will be a second coloring. It has, oh wait, I did something wrong. Oh yeah, sorry. it has 0 red P3s. So let's kind of count the differences between this coloring. This coloring has a red P3, and all other monochromatic subgraphs are just isolated vertices in this one. This one has 2 red P2s, and it has a blue P1. And again, aside from this, everything is just independent. So this is the kind of thing that this lemma says. It says that you can pick any path length, and you can get 2 colorings of a particular subgraph of a cubing graph, where the number of copies of this path length decreases by 1 between these 2 colorings. And aside from that, only the count of smaller paths change. So that's the kind of thing that this lemma says. And there's also another condition here that basically the boundary of the small graph you find doesn't change between the 2 colorings, which again, the boundary just means that the vertices of degree which don't have degree 3. So you say, what I've drawn for you here is essentially a proof of this lemma for graphs of sufficiently large girth. So if your cubic graph has sufficiently large girth, you'll find a copy of like a tree like this one, and a coloring like this one proves this lemma. If your graph has small girth, then the lemma is still true, but it becomes quite a lot more intricate to prove. So let me just briefly tell you how to kind of how things fit together. First, you use the first lemma to get your coloring C, let's call it C start, with the number of red paths being roughly equal to the number of blue paths. Then you use the second lemma to find many graphs or copies of a graph of H with 2 different colorings, C1 and C2. So this previous lemma, it only gives us, as I wrote it, only gives us 1 graph like this, but because it has bounded size, you can just pull out like linearly many of them. So H1, H2, up to H, let's say epsilon n. And then what you do is you recolor some of these using C1 or C2 to get rid of the error term. So I'm lying a bit here, but the intuition is because these 2 colorings, they change the counts of particular paths by 1. If you just like color the right number of these by C1 and the right number of them by C2, you can make the difference of the number of path counts as small as possible. That's kind of the idea of how to get this theorem. So let me finish with a couple of open problems. I think so. The kind of the 2 interesting open problems here are these 2 motivations, which I told you, the conjecture banlineal, which is a strengthening of Ando's conjecture, saying that you can get a partition into matchings. I don't think our methods are useful here, to be honest, because if you're trying to get matchings, you don't really have this kind of flexibility that we exploited for getting Ando's conjecture. So if this conjecture is true, I think it would require very different methods than the random ones we used. On the other hand, there's this conjecture wormhole that is essentially an edge coloring version of Ando's conjecture. And here, I think, although none of our methods directly apply to edge colorings, the setting is quite different. The conclusions you want in this wormhole conjecture are quite different. You know, you want these path forests, which we don't get. but I think all of the intuition of the proof I presented for you does carry through. So actually, while I was preparing this talk, I got a bit distracted thinking about Wormhole's conjecture, and I do think it's pretty doable. So if anyone here is like interested in collaborating on this conjecture, just shoot me an email and we can have a think about it. Okay, so let me finish here. So thank you.
Thank you, Alexey. Let's thank Alexey for a great talk and for potential collaboration with him.